Good day, folks. In this presentation, I would like to discuss uh, few tabs that appear in the Measure Inertia dialog box of the Catia V5 program. Uh, Let me remind you that Measure Inertia, it appears in this dialog box, which is Measure, and it looks like a weight here, as you can see. And when you click on that, you get a big dialog box, and part of it, the middle section of it, has several tabs in it. If you actually activate these things, let me tell you what I mean by that. To customize, to make sure that these are active, if the main dialog box that opens up, okay, there is at the very bottom right hand side, there is a customize button. If you click on it, it gives you a menu and you decide what is it that you want to activate, okay? So, for example, if you don't want inertia matrix with respect to P, let's say these things, if you don't want these things to be active, don't check them here. But anyway, let's move on. What I want to go is to go through these tabs and see exactly what they do to the extent that can be done in a relatively short period of time. Suppose you have a three-dimensional object bending it here right there, and then you ask someone to find the moment of inertia. And when you say moment of inertia, there is moment of inertia and there's a product of inertia, but that's okay, of this object. And of course, the response is going to be, you can't do it. I can't tell you. You better give me more information. And what exactly is that more information that you're talking about? First of all, as soon as you say calculate moment of inertia, you need to have given me some access system. Okay? Some access. And even then, depending on where the origin of that axis is, you get a different value. So you need two things: an axis system, which means three mutually perpendicular directions, and a point. As soon as you specify the point and that axis system, it assumes that the origin of that axis system is at that point. So in this particular setup, let me go back. In this particular setup, you can see that these things were not activated, but I will in the present exercise, and we'll move on. So we need an axis system, we need a point, and that means that as soon as I specify the point, it means that that axis system is originating from that point. Now you can go ahead and calculate the moment of inertia and product of inertia. Depending on the textbook that you use, moment of inertia is, of course, this calculation, and the product of inertia is over here, but Catia assumes that these have negative in front of them. Okay, but that's okay. That's really not the point of the tutorial. The moral of the story is that you could not have done this calculation without knowing what the origin is and what the access system is. It's only then that you can go ahead and calculate, do calculations. Here I've activated all of them, by the way. In the first two slides that I showed you, these three were not active, but here are active. So what does that mean? When you select a 3D object, when inertia, measure inertia icon has been selected, then this tab means that calculate those integrals, those moments uh, with respect to the point P being at the centroid, in the center of mass of the object. Okay? So if that point P is at the center of mass of the object and the coordinate system, without any further specification, is going to be using the global axis system at the centroid of the part. And you get 6 numbers. Okay? Now, when you select this tab, what it gives you, it assumes that you want to calculate the point P to be the origin of the part. Origin of the part. Remember, origin of the part is not the mass center of the part. It could be that the way you made it, it actually happens to be there. But generally speaking, the origin of the coordinate system, global coordinate system, we refer to it as O. And so when you select this tab, it gives you the values where the axis system is the original global one, and the point O, the origin, is the origin of the coordinate system. Okay? When you select this one, is that you go and pick a P, and without any further specification, the global coordinate system is going to be used. So that coordinate system is going to be the global one emanating from the point P, wherever you pick. Okay? All right. I'll come to that later in a minute. Let's go to this one. Axis system is when you actually go ahead and pick, you go ahead and create an axis system which may not be the global one. We'll do an exercise, we'll see how it goes, okay? Now, as far as this other one is concerned, you can find inertia, a moment of inertia with respect to a line or a direction, okay? So if you select this tab, it means that it's going to find the moment of inertia of the 3D object with respect to the direction that you picked. And that point O, incidentally, happens to be come out to be the midpoint of the selected line, for example, if that's what you did. We'll come to the examples. So there's some information about this moment calculate inertia in V5, and there's one in V6. And the example that I'm going to do for you is this. So I'm going to make a box 3 by 2 by 1, and make sure that when I make it, the origin of the coordinate system, origin of the part, is at one of the corners here. Okay. So let me assume that the density is 1 kilogram per meter cube. It's a very light box if you want. And then later on, I'm going to come and create an axis system like this and see how it comes into the picture when we use other tabs. Now, if you have a simple cube, the formulas for a cube for moment of inertia in the principal direction are given here, but then you have to use a whole whack of parallel axis theorem, both for the moment of inertia and the product of inertia, to do hand calculations. So the example that I'm going to show you can be checked, and I've checked it against these things and the parallel axis theorem, and it matches perfectly. Okay. And then I'm going to do an example of make a box for you, 1 by 1 by 1 meter, and find a moment, given a density of 1,000 kilogram per meter cube. We find the moment of inertia with respect to an axis that I have chosen to be this line. Okay, we'll do that later. All right, let's go ahead and do it. My units have already been set, so on this horizontal plane, I will sketch. I'll sketch a rectangle, 1 meter by 1 meter. Sorry, 3 meter by, okay, let me see what I have here. In the direction X, in direction Y is 3, that's good. So exit, yeah. And then we pad it by 1 meter. There we go. So what I have done here is create that box for you, and notice that the corner of the box that you can't see on the other side is at the global origin. All right, let's apply a material. So we go here to apply material. If I can find it here, there's apply material, click on it, select the part. I'll apply aluminum, but I'm going to change the density of it to be 1 kilogram per meter cube. Okay, so that's going to be 1. Good. So notice that this is what I wanted. Double check. Let's make sure it's correct. Yeah, 1 kilogram per meter cube. Good. All right. We're pretty much done. Now we're going to go to measure inertia, which is right here, measure, and this is measure inertia. You click on it, You select the part, three-dimensional object is selected. I have already, in my customization, I've selected everything so that these these tabs are all active. So when you look at the first one, notice that first of all, it shows you the center of mass is right there, and gives you the moment of inertia, both the moment of inertia and the product of inertia, with respect to this g. So the origin of the coordinate system to calculate those integrals is at the mass center, and the directions x, y, z are the global directions because I haven't done anything yet, anything about it. So there we are. And it's not surprising that the product of inertias are zero, because when the point P, or the point that's selected, is your mass center in this particular problem, x, y, x, z, and y, z, when the coordinate system is placed at this point, or planes of symmetry, and therefore the products of inertia are zero. So look, what we have done for the origin of the coordinate system, G is selected. G is the center of mass. And the directions, of course, are global x, y, z. So basically this thing that you see there. Good. Now, when you click on inertia with respect to O, that means that the point where the origin is selected, or the point where the axis system is erected at, is the point O global coordinate origin, which means that coordinate. So when I do that, things will change, and naturally, no longer x, z, y, z, and x, y are planes of symmetry, and therefore you have product of inertia right there. You can see that. Okay? Good. Now, if you click on inertia with respect to P, this means that you probably want to use a different point for the origin. For example, make sure you check the select point box. Let me go ahead, for example, and select this point. You see this point right in the corner? Right there. And what happens is that the point that you pick is that coordinates. And because we have not changed the axis system, it's the global axis system erected at that point. And you're going to get your moment of inertia and the product of inertias. Okay? Good. Now, let me go ahead and do this last one, because for the middle one, this one, inertia with respect to axis, I'll do a different example. So if you click on that, notice that you can go and select an axis system, but I don't have one. So I'm going to cancel that. Let me go and make an axis system first. So you click on the axis system. I'm going to make it at that origin being that point. And I'm going to line it up so that Z goes, let me see that. Z goes along. Okay, Z goes along. So Z goes along that line, but flip the direction. So it goes like that. I want Y to go on this line. Good. And X is going down. Good. And let me uncheck the current here so that this is the coordinate system that I've created. That's not a big deal. It's just that I don't want things to be in my current coordinate system, unless I really want it. Okay, so let's go ahead and click on this inertia, measure inertia, select the part. We already explored these, so we go to the inertia with respect to axis, the last tab. Select this axis, select an axis. And where's the axis? I'm going to select this axis that you see here, either from there or from the tree. So let me see, it's easier to paint from the tree. There. So what it really means is that my coordinate system XYZ is over here. The origin is right there. Okay. And I'm calculating the moment of inertia and the product of inertia with respect to this coordinate system, whose origin is right there. These numbers. Okay. That's good. So that the only thing that's left to do is this inertial axis, show you in an example. I can do it here, but I rather go to this example because we have an analytical value from, this is coming from Miriam's book, and whatever we get better match this. So let's go ahead here. Yeah. I'm going to start another file. And on that horizontal plane, I will sketch. And just to convince you that it doesn't matter how you draw this, I'm going to make a rectangle, weird rectangle like that, and dimension it to be 1 and 1. One meter. And dimension this to be 1 meter. Okay. So let's fit this and exit and pad it up by 1 meter. Pad it up or down, doesn't matter, up by 1 meter. Good. Because I want to select a direction here, so I'm going to make a line from this point to that point. Later on, I'm going to use this as the line along which the inertia is calculated. So apply material, again, dummy aluminum. I'm going to change its density to be 1000. Then say, okay, these things are irrelevant, I'm not using it. I just want the density. Incidentally, yeah, that's now, good. You click on this, click on that measure inertia of whole 3D object. This tab, the fourth tab from the left, select an axis. That means that direction. Select the direction that I picked right there. It tells you where the origin of it is. It's probably halfway between, it's a halfway point. That's really not the point. This is the direction of the line, and this is the value. Look, the mass moment of inertia about that line that I created is 166.7. 166.7. This is a theory. And the radius of gyration is square root of I, this I divided by the mass. Mass, because it was 1 by 1 by 1, with that density is 1000 and 0.408 meter. So if you go here, here's the radius of gyration, 0.408 meter. So I hope this becomes clear on what these tabs are, okay? There are some comments in the documentation about the be careful, because if you want to change the point and you don't actually select a new point, it uses the old one. And yeah, so you got to be careful about that. That's pretty much it. Good luck.